Hello everyone, in this video we're going to talk about classification problems. So the main difference between regression problems and classification problems is the y variable, the dependent variable. In regression, remember, our y variable is a numerical variable. It can be continuous, an integer number. When we're talking about classification problem, the variable that you want to predict, the dependent variable here, is not numerical. Typically, it's a categorical variable. So we will see some examples here of categorical variables. Here you want to get a model where you want to use some predictors, x variables, to predict the categorical variable y, one or more categorical variables. Okay, so there are different types of classification. So we have first binary classification. The binary is when you have only two possible outcomes. Your y variable is 1 or 0, or for example, in the email spam detection, let's say that there are two possible categories for your variable, for your y variable. So it can be a spam or not. That's what I mean by 1 or 0. In a medical diagnosis, if there are only two possibilities, disease or not disease, that's a binary classification. Of course, there are some cases in medical diagnosis that maybe there are three or more outcomes, right? Like, let's say no disease, like low level, medium level, high level. So then that's not a binary classification because there are more than two possible outcomes. So that will be then our second type of classification, the multi-class classification. Here is when we have three or more categories for our y variable. Some examples. This is a typical example that you will find. It's like in the handwriting digits recognition. There are 9 digits. There are 10 digits from 0 to 9. Then the possible outcomes, it's 10, right, for each digit. For document categorization, there are like multiple options. There is a document and you want to classify like from what area of knowledge is that a document of science, history, literature, or even more possibilities. So since there are multiple classes, that's like more than two. That's multi-class, not binary. Image classification means that you train a model to classify animals in a picture, in an image. There is only one animal per image, but there are like multiple possibilities, right? So in that case, for example, if the possible outcomes are cat, dog, bird, or any other animal, like more than two categories, then again, this is a multi-class classification. And finally, there is a multi-label classification. The difference between multi-class classification and multi-label is that in multi-class, there is only one, in one observation, there is only one label. I mean, there are multiple options, but there is only one label. At the end, you just classify using one category. But in the multi-level, one label. But in multi-level classification, is when in the same observation, you might have multiple labels or multiple classifications. So let me give you an example of that. Let's say you have an image, right? But in the same image, the same observation, there are multiple animals. Let's say there is a dog, but there is also a cat in the same image, right? So when you're doing the classification, you need to label twice that same observation because there is a dog and there is a cat. So that's a difference. The difference between multi-label and multi-class is that in multi-class there is only one label, and of course there are multiple options for that label, but there is only one. But in multi-label, there are like two or more labels per observation. Okay, here there are some examples of classification problems. The typical one that you will find is fraud detection. So typically banks are analyzing transactions and they check whether the transaction it's a normal transaction or if it's a like fraud. Then you can create a classification model to do that. And of course, there will be some independent variable, the features. There will be like the transaction amount, the location of the transaction, the time, right? Let me see some other examples. For medical diagnosis, I already mentioned this. Whether you want to classify whether the person, the patient, has a specific disease using some variables like the symptoms, medical history, some lab test results. Sentiment analysis is really common in social media to classify whether a post, for example, is it's like it's positive or if it's negative or it's neutral. So typically companies want to analyze the reviews of their customers, right? Like to get an idea of the sentiment. Okay, so having said that, let's go over an example. So I think we have used most of these libraries, but just to mention some of them, of course, Panda. We are always like importing files. Typically, you want to perform some EDA, so you use Pandas. In scikit-learn, it's really useful when we're doing machine learning, like regression, classification, clustering, dimensionality reduction. All right, so from here, we are importing our random forest, decision trees, but now the difference compared to our previous videos is that we were using random forest regressor, decision tree regressor, because our problem at that time was regression, right? But here it's a classification problem. The outcome is different. So you can use regressors here. It's like decision tree classifier. And if for some reason you made a mistake and try to use a decision tree regressor, when you're training the model, you will get an error because the y variable is not numerical. So scikit-learn will let you know that you're making a mistake. All right, let's talk about a little bit about our data set. In this case, we're getting the data set from scikit-learn. If you check here, this here data sets, we're importing it from scikit-learn. There are multiple toy data sets in scikit-learn just to learn regression, classification, you know, the different problems. Okay, so this data set, I don't believe it's a real one. I think it's a toy data set. It's about breast cancer. So once you import this data set, you get a dictionary. So this is the data, right? Multiple numerical variables. This is the target variable. It's binary, 0 and 1. I will show you what is 0 and what is 1. Here. 0 means malignant, that the tumor is malignant, and 1 is when the tumor is benign, right? So those are the two options. So 0 is pretty bad, 1 it's okay, right? That's the idea. Please remember the dictionaries, right? We have the key and the values, right? So target names here is the key, and the values here is this array with the possible values. We also have description of the data set, and the variables, of course, the independent variables. I won't go over all of them, but I just want to give an idea of the features that we're using here. So we have the perimeter, the mean perimeter of the tumor, the compactness, symmetry, texture, smoothness. So there is mean value, the standard error, or the worst value. So there are around 30 metrics. You know, it's just about the geometry of the tumor in order to make the prediction to see whether it's benign or malignant. So here we have the class distribution. We know that in our observation there are 212 malignant tumors and there are 357 benign tumors. We also have the information about the data set, how it was created. Okay, we have the feature names here. Again, this is another key value pair. And this is the array with the names, right? For the, yeah, I think there are 30 independent variables. Okay, so before we jump into like creating our classification model, so first thing, remember, if you notice our y variable here, it's like if it's malignant or benign. So immediately you know that this is not numerical, right? It's categorical. So what you're trying to predict is like, okay, if there is like a new patient and you know like these variables about the tumor, so you want to make a prediction to see whether the tumor is malignant or benign. So that's the whole idea of our model, right? So again, our y variable here, it's not numerical, it's categorical, right? Because the outcome, the output, it's categorical. All right, so you can perform an EDA. You always have to do an EDA. Sometimes I will skip the EDA just because, yeah, I need to focus only in the new part, right? The model, But again, this is a required step always when you are doing data science. Okay, so here we're just assembling a data frame with our data. So with the X variable, Y variable. So this is the data frame. So I guess for you, you will be more familiar with data frame instead of dictionary, but the dictionary is fine. You can use it. Okay, so this is a quick analysis just to compare, like here y equal to 0 means malignant tumors, right? And I'm using the describe method just to see some descriptive statistics, right? So we have the mean value, standard deviation for the different variables. For example, the mean radius it's 17.46 for the malignant, and similar analysis can be done for the benign tumors when y is equal to 1, right? So if you notice the difference here, it's this one, the mean value for the mean radius, it's 12.14. So it's lower, right? It's lower. It's from 17.4 to 12.14. So there is a difference. And you can do the same analysis for the other variable, right? To see whether there are differences or not. So I'm just trying to do like a description or analysis for each category, and I'm trying to understand if there are some differences between the two categories based on the values of their multiple variables. So that's that would be my initial approach to perform EDA here, just to compare some basic descriptive statistics for the different variables, just to see whether initially I can identify if there are some differences. So immediately, for example, I can just with the first variable, I can claim, at least that would be like hypothesis. It's not like a final conclusion, but my initial hypothesis is like and maybe it makes sense, right? That malignant tumors are bigger than benign tumors, at least because the mean radius it's smaller, right, for the benign tumors. It's 12.14 compared to 17.46. But again, remember, during the EDA, you don't make conclusions. It's just about making hypotheses, right? And then you need to run some analysis to confirm that. A similar way to compare this is just by using plots. So I'm using a box plot here to compare the mean radius. Why is the mean radius here? I want to see like if it changes based on the outcome on the y variable. So here we have the mean radius, and we have two box plots, right? The first one for the malignant tumors, for y equal to 0, and the second one for y equal to 1, that's for the benign tumors. So we're comparing the mean radius for the different observations in our dataset. And you can see that it looks like there are some differences. Remember that the line inside the box is the median value. So for sure the medians, they look different. Please notice that in the case of the benign tumors, values are, in general, I would say they are smaller compared to the mean radius of the malignant tumors. So at this point, I will know for sure that if we create like a classification tree for this problem, I'm pretty sure that mean radius, that variable, is going to be in our tree for sure, because you can see that there is a difference, right? So most likely our models are going to use this variable and other variables, of course, to classify the observation, the tumors. Okay, I'm going to create a tree. Again, I have mentioned this before, but I think it's important to emphasize that one more time. I like to use trees, and my advice for you is to use trees not just for prediction purposes, but also during an EDA to understand your variables and the context. So here, we're creating a decision tree classifier. I'm training the model. I'm not splitting because, again, at this point, I'm not like I'm not using that tree to make predictions. It's just to understand and get some insights, right, from our data. Okay, so this is the figure. Here we create the tree, same as during the regression analysis, the name of the model, future names, and that's it. So let's see what we get. So our tree is placing on top of the tree. The first node is the worst radius. So what it means is that this is a critical variable, like the most important variable according to the tree to classify the observations. So it's saying that the worst radius if it's smaller or equal than 16.79, if it's true, you go to the left. If it's higher than this, you go to the right, right? So before I keep moving in the tree, let's understand a little bit more this other information. Here we have a Gini metric. A Gini metric is a metric that is used in economics just to measure inequality. It's a metric between 0 and 1. So if the value is close to 0, it means that you have like inequality, like huge inequality. Now if it's close to 1, it means that like all classes are equally distributed, right? That's the idea. Now, since we want to classify, we want to minimize the Gini. So I want to see like high inequality. That means that I want to find a way or a combination of variables that is going to help us to classify perfectly, or not perfectly, but at least in a good way, the different observations. So you will see that as we go down in our tree, the Gini metric, it will decrease, right? Because our tree is going to start classifying. So initially, the value here refers to the how many observations are zeros and how many observations are 1. In other words, we have 212 observations that are malignant tumors and 357 observations that are benign tumors, right? Okay, so if the Wurtz radius is less or equal than 16.79, so you go left. And please notice, and I believe that this makes sense, so if it's smaller than this, if the Wurtz radius is smaller than this, then we get, please notice here in this node now, there are the number of or at least the proportion of the number of malignant tumors has decreased. It's 33 malignant tumors and there are 346 benign tumors. And of course the Gini is decreasing here because it's starting to classify. So it's identifying that if the Wurtz radius is more than 16.7, then a high percentage of the tumors are going to be benign. Now let's see the opposite. If the Wurtz radius is greater than 16.7, so if the tumor is bigger, then please notice here that the value, most of the observations now here are equal to 0, meaning that most of the observations in this node are malignant tumors. So here we have 179 malignant tumors and there are only 11 benign tumors. So the Gini again is decreasing. Initially it was like 0.468 and now it's 0.1 because it's classifying. There is like inequality. So there are like more observations in class 0 compared to class 1. It means like initially they were like not evenly classified, but at least they were like close to each other, relatively speaking, compared to what we're seeing now. But as we start our classification, you can see that now the inequality is higher, or the classification is better. So you start like getting a more clear picture of what variables are relevant to classify your observations here in this problem. Now, for EDA purposes, what you can do is that you just go to the bottom of the tree, to the leaves, and you check like, okay, where are the most of the observations for each class. So we know that initially there are like 569 observations. Okay, so if you, for example, here in this leaf, there are 332 observations, like more than half. So there are a lot of observations here. But that's not it. If you notice, from the out of these 332 observations, most of them, like 328, are benign tumors. There are only 4 malignant tumors. So now it's important to understand why, like what combination of variables will get you most likely a benign tumor. So this is information. This is the insights that we're getting from our EDA using the tree. So okay, let's like go. Let's check the tree and see how can we get there. Okay, if the Wurtz radius is less than 16.79, okay, we go to this part. If the Wurtz concave points is smaller than 0.136, continue here, and the Wurtz fractal dimension, I don't know, to be honest, I don't know what is the mean of this metric. If it's greater than 0.055, then we get to this point. Now, why this is relevant? Because you start getting insights about the benign tumors. So you can know that with these 3 variables, at least you get an idea of for which values your tumor most likely is going to be benign. A similar idea will be for the for the malignant tumors. So we identify here in this leaf, I have 172 observations, and almost most of them, almost all of them. Here we have like 171 malignant tumors, and there is only one benign tumor. So this is relevant, right? Let's see what are the variable combinations that will get you a malignant tumor. So if the Wurtz rate is greater than 16.7, if the mean texture is greater than 16.11, and then if the Wurtz smoothness is greater than 0.08. So if that occurs, then most likely you're analyzing or you're getting a malignant tumor, right? Because most of the observations are here. So this is how, the knowledge that you can get from the tree. It's difficult to get this knowledge just by looking at the initial plot, like box plots, because in the box plot you can see some differences. You can say, oh, there are differences. But here, not, you cannot just see difference. You can see like for which values of the variable, and that's important. Okay, so once you are done with your EDA, now we can perform our like let's create our predictive models. So remember, we need to split our data, train, test. So here I'm splitting 20% for the test and 80% for the training. Here we're using the same function, the same method, train, test, split. It's not changing, it's the same regardless you're using classification or regression or any other problem. Now let's do some cross-validation. Remember K-fold cross-validation. If you don't know what I'm talking about, please go back to the previous video, and yeah, in the previous week we discussed about cross-validation, K-fold cross-validation. So here this is for the classification for the initially for the tree, and the metric that we're getting here is the accuracy. So what is the accuracy? It's just the percentage of observations that are being classified correctly. So here is like 0.92%. It means that from the training set, not from the training set because this is a cross-validation for the, let's say for the average. Remember here that we're getting, if I run this, I get five accuracy metrics. So for the first one, the 94% of the observations were classified correctly. For the second one, 93% of observations of the evaluation set were classified correctly, right? So that's what I'm getting, the percentage of observations that were classified correctly by our model in the different validation sets, right? So on average, that was 0.93 or 93%. Now in the case of the random forest, it was slightly higher. Remember that these numbers may change in your case. I mean, if you run this, you may get different numbers because when you're performing the split, typically this is done randomly. Typically no, it's performed randomly. There are some ways to get the same numbers, but I mean, it's just you can add more parameters. There is like a set seed or no, it's random state. It's the random state, I believe. Yeah, random state. So you can, if you want, you can use the random state. The set seed is in R. The random state, let me change the language. Yeah, the random state, and you use any number, like 1, 2, 3, that's fine. As long as we use the same random state, like the same number here, this will set the same seed for the random generation numbers, and we should get the same numbers. But again, this is just a way to give like more reproducibility to your code. Here for me, it's not relevant, but if you want to get the same numbers always, let's say that you're analyzing some data and you want to get exactly the same result always, then you can set the random state to a specific number, and you consistently you will get the same number. All right, so we're performing cross-validation for both, for the random forest and the decision tree classifier. I'm not typing the code because we have done this before. That's why I'm giving you the code. Okay, so we said that random forest, it's showing like a higher accuracy on average. Yeah, there's a small difference, but there is a difference, right? Then let's say that this is the winner. I'm gonna pick random forest as my model or my algorithm to make predictions. That's why I remember that after the cross validation, then we train the final model. So using the training data, we create our random forest, right? That will be our model. And then we compare the accuracy of the model, like for the training set, but this is important analysis also for the test set, because this is new data. Remember that the test set, we didn't use that one in the cross-validation stage. So it's important to see if it's consistent. So here we have a difference within the 10%, the difference. So I'm okay with that. And again, it's normal that it's gonna drop a little bit. The problem is if it drops, like there's a huge drop. Let's say like this is 98%, and then it tested is 60%. So then you can feel that maybe there is some like overfitting in your analysis. But here again, it's like within the 10%. So it's fine. It's fine. Okay. The accuracy metric, it's interesting, but you cannot make a decision to see if a classification model is good just by looking at the accuracy. So you gotta be careful. This is just part of the picture, part of the analysis. But again, you cannot make a decision entirely based on the accuracy. I'll show you why. There are more metrics, so I'm gonna mention two more metrics: recall and precision. So how can I get recall and precision? So this is a method that will get you everything. The classification report from scikit-learn, it has two outcomes. The y test, which is the real values, right? That's y. And then y hat, right? The predictive values. So you get those values with the model. That's why model one dot predict, and using the x test. So this is y hat. So here you're comparing, you're providing the real value and the predictions, just to see the errors and these metrics. So let me show you how to get this. Let me give you an idea. So the first thing that you need to know is that there is something that is called the confusion matrix. The confusion matrix. The confusion matrix, we analyze our classes and we see the real values and the predictions. So here the PDCross tab is creating just a table where my rows will be the y hat, the predictions, and my columns are the observations. So again, columns observations, this is y, and in the rows this is y hat, right? This is y hat. Now, this is the confusion matrix for the test set. So how can I get the accuracy? So the accuracy, it's the number of it's the percentage of observations that were classified correctly. So in this diagonal, I have the observation that were classified correctly. For example, this 37 observation refers to the malignant tumors that were classified correctly. So remember, this is the row is y hat and the column is y. And the 66 refers to the benign tumors that were classified correctly. This is where you have the match, 1 and 1. It's the match, right? You see, 0 and 0, right? In this diagonal will give you the accuracy. So if you measure the accuracy, will be 37, like manually. It's 37 plus 66 divided by all the observations, 37. I mean, there are better ways to do this. I just want to show you like how to get the numbers to understand this a little bit more. And 66. So this is the accuracy, 0.90. 90% of the observations were classified correctly. I believe that we get this number here. The accuracy of the test is 0.9035, right? So here we're getting the 0.9035. You see, it's the number of observations that are classified correctly. But if you want to judge a model, again, you need more information. It's not just about the accuracy. So let's measure now the recall. The recall is the number of observations classified correctly per class. So for example, for 0, for the malignant tumors, just think how many malignant tumors are in our test set. Remember, this is y. The y is the column. So there are 37 plus 7. This column, 37 plus 7, that's the number of malignant tumors. And how many of those were classified correctly is 37 divided by the total. So let me get the number. It will be 37. That's the accuracy. Plus divided by 37 plus 4. So this is recall. This is the recall. So it's the number of observations classified correctly per class. The accuracy is, for the whole model, for every single class, but the recall is like the accuracy per class, just to be more specific. So 37, I don't know why I type it's 7, right? I said 7 here. It's the column. I'm sorry, it's the column. 37 plus 7. So this is the recall, and you have it here, right? The recall for class 0 is 0.84, right? So it's the column, right? Observations that were classified correctly for that class divided by the total number of observations of that class, 37 plus 7. That's how you get the 0.84. And same thing, the recall for value equal to 1 for the benign tumors. It's 0.84, the recall. Let's see how we get that number. So just by checking at the column, right? So how many observations, how many benign tumors were classified correctly? 66. Out of how many? 66 plus 4, 70. So again, we're getting the 0.84 and the 0.94. That's the recall for class 1 or for the benign tumors, right? So the recall metric typically is referred as a metric of quantity, frequency, like how many were classified correctly, right, from the observations in your data set. It's an important metric for sure. In some cases, for the binary scenario, binary classification, instead of recall, you will see like sensitivity and specificity. That's the way that is referred, but it's the same metric, sensitivity and specificity. I prefer to use the terminology of recall because this is a general terminology. That means like if you have 3 classes, 4 classes, 10 classes, like 0, 1, 2, 3, 4, 5, again, it's just recall for class 0, recall for class 1, recall for class 2. But the sensitivity and specificity words, they apply only for the binary scenario. So yeah, in general, it's better to just talk about recall instead of just sensitivity and specificity. Okay, so this is a metric of quantity, frequency, and then we have precision. This one measures the quality of your predictions. Some authors may mention that this is the probability that your prediction is right. That's the way they define this. It's the quality of your prediction. So here we measure per row. That means like we measure per row. Okay, so you want to see like what was the quality of the prediction of your model. For example, for zeros, you predicted 37 correctly, but now how many predictions of 0 you did, or the model did? So it's 37 plus 4. So let's measure the precision again. That's the quality of your precision, of your prediction. So there will be 37. It's giving me here the numbers. 37 divided by 37 plus 4, and 66 divided by 66 plus 7, the row. So again, this is like number of zeros that were predicted correctly out of the number of zeros that were predicted, right? So you're measuring the quality of the prediction. So this is like if the model says something, if you should believe it or not. That's pretty much the idea. It's interesting because you can have a low precision and you can have high recall at the same time. It sounds weird, but that's a model that says, okay, this is the class, this is the class, this is the class, this is the class. So let's say that the model is predicting a lot of times, for a lot of observations, predicting the same class. So that model will most likely will classify correctly those observations, but the problem is it will make some errors. So the recall will be fine, but the precision is going to be low because the model is saying the same thing always and always, every single time. Again, it's gonna be correct in the recall, but the problem is that the model, if it's saying that okay, this observation is this class, the precision is going to decrease because there can be some mistakes over there. So it's possible that you have in some scenarios that you have a high recall and small precision. We will see that later, but keep in mind. Now, I don't want to say here that one metric is better than the other. Actually, a good model, the idea is to have like a balanced model, to have like good recall for every single class, high precision for all classes. But in real life applications, sometimes there are some classes that are more important than others. For example, if you are in the fraud detection, let's say a bank is analyzing transactions, I'm pretty sure that as a customer, you want that model to be really accurate for the fraud transactions. It's better to get some uh, errors. Let's say that you get a message or asking whether you're making the transaction. It's I think for the customer it's better to say, yeah, this transaction is fine, but you don't want like a fraud to go like undetected here. So in that scenario, the model you want to have like a recurrent precision, especially for that specific class. Okay, so yeah, this is the our first introduction to classification. So with this we have completed regression and classification. And now in our next videos we will go over clustering analysis. I'm giving you the introduction of like the most important problems in data science using Python, and then we will go over same problem using R. Okay, I'll see you in the next video.